the last video in the three-phase induction machine course. I presume that you covered all the videos, so it's time now to test yourself and test your knowledge about the three-phase induction motor through this quiz. To get the most benefit from this quiz, let me give you some tips before you start. You need to prepare this stuff before you start. So you need pen and paper or pencil and paper, your calculator, and if you like to use your headset, it's up to you. If you don't like to use this stuff, you can use your tablet and pen and paper beside you as well. So your tablet can be used as a calculator. If you like, you can put stopwatch beside you. Nevertheless, the questions are timed. During the quiz, you need to avoid any distractions like your phone, your social activities, eating, drinking, or any noise beside you, so you need to dedicate the time for this quiz. Also, it's not nice to set something like this picture, so you need to focus and set in your desk to get the most benefit from this quiz. So what is the quiz structure? The quiz consists of 15 questions. The questions format include multiple choice questions, MCQ, calculated formula, multiple answer questions, true and false, and hotspot. So what's hotspot? For example, if we have a picture for the machine structure, you are going to assign whether the state or rotor or something like that. Each question is timed according to its difficulty level. For example, some questions may have 20 seconds, other maybe 1 minute. Once you finish the questions or the quiz, you are going to find the detailed answers and feedback so you can make a self-assessment. So each question is scored out of 10, so you are going to have a score out of 150. Send me your score through the video comments. To be well organized, I'm going to give you an advice. I'm going to provide here the answer sheet for this quiz. So the quiz consists of 15 questions, as you can see here. So question number, the type of the question, and the time for each question. So for example, question number 1 is MCQ, 15 seconds, and you are going to choose between A, B, C, and D, and so on for other questions. So my advice to you either to take a picture for that one and print it, or you are going to copy that one in your paper. I presume you are ready now, so the quiz will start in 5 seconds. Question number 1. The produced electromagnetic torque in the three-phase induction motor depends on A. Saliency, B. Saliency and induction, C. Induction, D. Saliency or induction. Time starts now. Question number 2. The field nature of the three-phase induction motor is A. Stationary, B. Pulsating, C. Rotating, D. Traveling. Time starts now. Question number 3. Which of the following represents the rotor of the squirrel cage induction motor? A, B, C, D. Time starts now. Question number 4. The figure shown below shows the structure of the three-phase induction motor. Select the numbered circle which represents the armature winding. Time starts now. Question number 5. A 4-pole three-phase induction motor fed from a 50 Hz supply and running at 1425 RPM. The slipping percentage is A 4%, B 5%, C 4.5%, D 5.5%. Time starts now. Question number 6. A 400 volt line RMS 50 Hz 3-phase 4-pole induction motor operates at a speed of 1440 RPM. The stator losses are 400 watts. If the developed torque is 55 Newton meter, calculate the motor efficiency in percentage and neglect rotational loss. Time starts now. Question number 7. 3-phase 50 Hz 4-pole induction motor has rotor resistance 1.4 ohm per phase at standstill and rotor reactance of 5.8 ohm per phase. Calculate the maximum torque in Newton meter if the developed torque is 69 Newton meter when the motor operates at a speed of 1444 RPM. Note, stator impedance is neglected. Time starts now. Question number 8. A 4-pole 220 volt delta connected 50 Hz 3-phase induction motor load has the following parameters per phase at standstill. R stator equals 1.2 ohm, R rotor equals 2.2 ohm, X stator equals X rotor equals J 3.6 ohm. Using the approximate equivalent circuit, calculate the starting phase current in polar form, magnitude and angle, to 2 decimal places. A. 27.63 and angle minus 64 degrees ampere. B. 47.85 and angle minus 64 degree ampere. C. 15.95 and angle minus 94 degree ampere. And D. 47.85 and angle minus 34 degree ampere. Time starts now. Question number 9. A 220 volt phase value 50 Hz 3-phase 4-pole star connection class A motor gave the following DC test results. VDC equals 12 volt, IDC equals 2 ampere. The stator resistance per phase is A 6 ohm, B 3 ohm, C 3.33 ohm, D 6.66 ohm. Time starts now. Question number 10. A 220 volt phase RMS 50 Hz 3-phase 4-pole star connection Class B motor gave the following locked rotor test results. V locked equals 50 volt phase value, I locked equals 10 ampere, and B locked equals 900 watt. The stator resistance per phase is 0.6 ohm. The rotor resistance per phase at standstill is A 3 ohm, B 2.4 ohm, C 2.88 ohm, D 9 ohm. Time starts now. Question 11. A 220 volt 50 Hz 3-phase 4-pole delta connection Class B motor gave the following locked rotor test results. V locked 50 volt, I locked 10 ampere line value, and B locked 450 watt. Calculate the motor equivalent reactance per phase. Time starts now. Question 12. Figure 1 shows the torque time and speed time characteristics, while Figure 2 shows the current time and speed time characteristics. The motor is started using direct online starting. A true, B false. Time starts now. Question 13. The three-phase induction motor requires a speed control technique. Which technique or techniques from the following can be used for the squirrel cage induction motor? Note it's a multiple answer question. A. Stator voltage control. B. Rotor voltage injection. C. Star delta switch. D. Adding rotor resistance. E. Pole changing. F. Variable voltage variable frequency control. Time starts now. Question 14. The manufacturer delivers the following information regarding a three-phase induction motor. The motor full load slip is 3.5%. The motor starting current is 55.4 ampere. The motor full load current is 11.3 ampere. The starting torque is 120 Newton meter. The full load torque is 47 Newton meter. Based on this information, select the most appropriate motor class. Class A, Class B, Class C, Class D. Time starts now. Question 15. As a design engineer, you are tasked with selecting the most suitable design class for a three-phase induction motor to be used as a driver for a jet bridge, as illustrated in the figure. The answer is Class A, Class B, Class C, or Class D. Time starts now. The quiz is finished. Now it's time to look for the model answers and feedback, and also you can make a self-assessment. Let's start. Question number 1. The produced electromagnetic torque in the three-phase induction motor depends on saliency, and induction, saliency or induction. So the answer is C, induction. The torque produced in the three-phase induction motor depends on induction torque. To know more about that one, please visit the video Induction Machine Course Chapter 0 video number 3, Magnetic Circuits and Torque Production. Question number 2. The field nature of the three-phase induction motor is A. Stationary, B. Pulsating, C. Rotating, D. Traveling. So the answer is rotating. So the field inside the induction machine, or the electromagnetic field inside the induction machine, is rotating field. If you'd like to know more about the field inside the induction machine, please visit the videos Induction Machine Course Chapter 1 video number 1, Rotating Field, Induction Machine Course Chapter number 1 video number 2, Synchronous Speed and Field Nature. Question number 3. Which of the following represents the rotor of the squirrel cage induction motor? A, B, C, D. So the answer again is C. So A represents stepper motor, B represents slip ring induction motor, C represents squirrel cage induction motor, and D represents a stator of induction motor or synchronous machine. So the rotor of the squirrel cage induction motor is represented by part C. If you like to know more about that one, please visit the video Induction Machine Course Chapter 2 video number 1, Unveiling the Secrets of Induction Motors. Question number 4. The figure shown below shows the structure of the three-phase induction motor. Select the numbered circle which represents the armature winding. We know that the armature winding in the three-phase induction motor are in the stator, not in the rotor. So I'm going to exclude these parts. So I'm going to focus on the stator. So number 1 represents the stator yoke or outer stator frame. And number 2 represents the armature winding, the three-phase winding. Number 3 represents the teeth. Number 4 represents the slots. So the answer is number 2. If you'd like to know more about the structure of the induction motor, please visit the Induction Machine Course Chapter 2, video number 1, Unveiling the Secrets of Induction Motor. I'm going to advise you to look for all the numbers. So what's number 10, what's number 9, what's number 8, and so forth. Question number 5. A 4-pole three-phase induction motor fed from a 50 Hz supply and running at 1425 RPM. The slip in percentage is, we know that the frequency equals 50 Hz, so that one is Fs, I call it Fs, and Nr equals 1425 RPM. And this machine is 4-pole, so the number of poles is 4. So we can calculate the synchronous speed, which equals 120 Fs over P. So that one equals 1500 RPM. So S equals Ns minus Nr over Ns. So that one will be 1500 minus 1425 over 1500. So that one will be 75 over 1500, which equals 0.05 or equals 5%. So the answer is B. The slip percentage is 5%. So if you like to know more about that one, please visit the video, Induction Machine Course Chapter 2, Video 2, Induction Machine Terminals and the Slip Speed Calculation. Question number 6. A 400 volt line RMS 50 Hz 3-phase 4-pole induction motor operates at a speed of 1440 RPM. The stator losses are 400 watt. If the developed torque is 55 Newton meter, calculate the motor efficiency. The motor efficiency is power output over power input. And here he said neglect rotational loss, so power output should equals power developed. And we know that power developed equals torque multiplied by omega r, torque developed. So that one is given 55. Omega r equals 2 by nr over 60. So that one will be 55 multiplied by 2 by 1440 RPM over 60. So that one give you answer that's 8293 watt. So we need to calculate power gap. So you need to return back to the power flow diagram. So we know that B developed equals B gap 1 minus S. So we know how to calculate S from the previous example, that we know that S equals NS minus NR over NS. NR is given. NS you can calculate it under 20 Fs over P, 1500 RPM. So S in this problem is 0.04. So we can calculate power gap. So power gap in this case will be 8638.54 watt. A B gap plus stator loss can give you P input. So P input equals B gap plus stator copper loss. So that one will be 9038.54 watt. So efficiency in this case will be the answer here, 91.75%. If you'd like to know more about the power flow diagram, please visit the video, Induction Machine Course Chapter 3, Video number 1, Power Flow Diagram and Motor Efficiency. Question number 7. 3-phase 50 Hz 4-pole induction motor has rotor resistance 1.4 ohm per phase at standstill and rotor reactance of 5.8 ohm per phase. Calculate the maximum torque. So we need T maximum in Newton meter. If the developed torque, so we know developed torque equals 69 Newton meter. When the motor operates at 1444 RPM. So this torque is given at this speed. Note stator impedance is neglected, and this is a clue point for this problem. If the stator impedance is neglected, so we can say torque developed over torque maximum equals 2S maximum over S square plus S maximum square. So we know torque developed and we know the speed, so we can calculate the slip. S equals NS minus NR over NS. So we can calculate S from this case. What's S maximum? S maximum equals R rotor over X equivalent. So we can calculate S maximum. So we know S maximum, we know S, we know torque developed, so we can calculate T maximum from this problem. The answer will be this one, 165.95 Newton meter. If you like to know more about how to calculate the starting torque, the maximum torque, if the impedance, if stator impedance is neglected or not, please visit the Induction Machine Course Chapter 3 Video number 2, Torque Speed Characteristics, and the Induction Machine Course Chapter 3 Video number 4, a comprehensive example of three-phase induction motor performance. Question number 8. A 4-pole 220 volt delta connected 50 Hz 3-phase induction motor has the following parameters per phase at standstill. R stator, R rotor, X stator equals X rotor equals J3.6. Use the approximate equivalent circuit you need to calculate the starting current. So we are going to put the equivalent circuit R stator, Jx equivalent, R rotor over S. So that one will be 2.2 over S. That one will be J7.2, which is 3.6 plus 3.6, 1.2. And the voltage here is V phase equals 220 volt angle 0. So the current for this machine at any slip, phase current, will be V phase over R stator plus R rotor over S plus Jx equivalent. And that one gives you the current magnitude and angle because he wants the current magnitude and angle. But if he wants the magnitude, so you are going to say that's I equal V phase over root R stator plus R rotor over S square plus X equivalent square. But he wants magnitude and angle, so we need to use the phasor form. So we are going to substitute here. That one is 220 angle 0. This machine is delta connected. V phase equals V line over 1.2 plus 2.2 over 1 because we have slip equals 1 at starting, J7.2. We need to calculate that one to change that one from rectangular to polar, and then we calculate the current. So we are going to find the current as a value. I calculated here, so that one will be 27.64 angle minus 64.72. What's the most appropriate answer here? Are going to have A is the best answer. So that one is 27.63 angle minus 64 degrees ampere, but that one is 47, that one is wrong, 47 is wrong, and 15 is wrong. If you like to know more about how to calculate the starting current or the current of the machine, you can look for the comprehensive example of three-phase induction motor, chapter 3, video number 4. Question number 9. A 220 volt phase value, 50 Hz, 3-phase, 4-pole star connection, Class A induction motor gave the following DC test results. We have VDC, we have IDC. The stator resistance per phase is, so we know that for star connection, RDC equals VDC over IDC, so that one will be 12 over 2, give you 6 ohm. But because we have star connection, so R equals RDC over 2, so that one will be 6 over 2 equals 3 ohm. But the skin effect, so R stator should equals 1.11 R, so that one 3 multiplied by 1.11, that one equals 3.33 ohm. So the answer is C. So if you like to know more about Turner's ratio and how to calculate the DC test, please visit the video induction machine course, chapter 4, video number 1, Turner's ratio test and DC test. Question number 10. A 220 volt phase RMS 50 Hz 3-phase 4-pole star connection Class B induction motor gave the following locked rotor test results. V locked phase value 50 volt, I locked 10 ampere and P locked 900 watt. The stator resistance per phase is 0.6 ohm. So he wants the rotor resistance per phase at standstill. So we know that P locked equals 3I locked square R equivalent. So R equivalent equals 900 over 3, 10 square. So the answer is 3 ohm. But R equivalent equals R stator plus R rotor. So R rotor equals 2.4 ohm per phase. So if you like to know more about testing, so please visit the video Induction Motor Course, Chapter 4, Video number 2, No Load, Inertia, Core Loss, and Blocked Rotor Tests. Question 11. A 220 volt 50 Hz 3-phase 4-pole delta connection Class B induction motor gave the following locked rotor test results. V locked equals 50 volt, and phase voltage equals line voltage. I locked line value equals 10 ampere, and P locked equals 450 watt. We need to calculate the motor equivalent reactance per phase. So we know that Z equivalent equals V blocked over I blocked. Blocked or locked, they are the same. So that one is 50 over 10 over root 3 phase value. So that one is 5 root 3 equals 8.66 ohm. But we need to calculate R equivalent, and R equivalent equals B locked or blocked over 3 I blocked square. So that one will be 450 over 310 over root 3 square. So that one gives you 4.5 ohm. X equivalent equals root Z equivalent square minus R equivalent square. So in this case, you are going to find that one root 8.66 square minus 4.5 square, and that one equals 7.4 ohm. So again, if you like to know more about the machine testing, you need to visit the Induction Machine course chapter 4, video number 2, no load, inertia, core loss, and blocked rotor tests. Question 12. Figure 1 shows the torque time and speed time characteristics. Figure 2 shows the current time and speed time characteristics. The motor is started using direct online starting, so definitely the answer is false, because as we can see here, the frequency changes at the starting point, so the machine is operating under soft starter or soft starting techniques. So please visit the video Three-Phase Induction Motor, Chapter 6, video number 1, Starting Techniques. Question number 13. The three-phase induction motor requires a speed control technique. Which technique or techniques from the following can be used for the squirrel cage? So we need to look for the squirrel cage induction motor. It is a multiple answer question. So stator voltage control, we can access the motor from the stator. Rotor voltage injection is not accepted because squirrel cage is not accessible from the rotor side. Start data switch, that one is a starting technique, not a speed control. Adding rotor resistance, that one is not accepted because that one for the slip ring induction motor. Pole changing, that one can give you multiple speeds or discrete control. Variable voltage, variable frequency. So the answers are A, E, F. To know more about speed control, please visit Chapter 6, video number 2, Speed Control Techniques. Question number 14. The manufacturer delivers the following information regarding a three-phase induction motor. The full load slip is 3.5%. The motor starting current is 55.4 ampere. The motor full load current is 11.3 ampere. The starting torque is 120 Newton meter, and the full load torque is 47 Newton meter. So based on this information, we need to select the most appropriate motor class. As the motor is operating at slip 3.5%, so class D is going to be excluded. So we are going to choose between A, B, and C. The ratio between starting current and full load current is around 4.9, so class A will be cancelled. So we are going to choose between B and C. The ratio between starting torque and full load torque is 120 over 47, around 2.55, so we need a high starting torque, so definitely our choice should be class C. So the design class should be class C, as the motor requires high starting torque compared to the full load torque and should operate with high speed. So if you'd like to know more about classes or induction motor design classes, please visit the video Induction Motor Design Classes. The last question, question number 15. As a design engineer, you are tasked with selecting the most suitable design class for a three-phase induction motor to be used as a driver for a jet bridge, as illustrated in the figure. So as we see here, that one should be very low speed, but needs at the same time very high torque. So the choice should be class D. The design class should be D, as the motor requires high starting torque and should operate with low speed. If you'd like to know more about induction motor classes, please visit the video Induction Motor Design Classes. This is the end of this video and the end of this course. I hope you enjoyed the course and thank you for watching. See you in the next course.